Welcome to the special edition episode of Beyond the Forecast. We've been going through some of the things that they're working on at NASA's Goddard Space Flight Center in Greenbelt, Maryland. We got a chance to see the Dragonfly mission that's going to Titan. If you didn't see that, check out that episode on Wavy Plus. But this one is all going to be about the Nancy Grace Roman Space Telescope. And when we were at NASA Goddard, there was a huge group of us. We got a chance to see not just the telescope, you can see that right here, but also we got a chance to tour different areas. So on our way to see Nancy Grace Roman Space Telescope, we had a chance to see some of the testing that the spacecraft had to undergo, including the Space Environment Simulator. Think of it as a giant vacuum chamber that is able to simulate the vacuum of space. It's a huge area. You can kind of get the sense of scale here with people walking around it. We also saw an acoustic chamber where the spacecraft and the telescope is exposed to very loud sounds because those occur during launch. So we want to make sure when things are pulling 100, 120, 130 decibels, when they're screaming loud, that the spacecraft, the vibrations from those sound waves doesn't shake anything loose. So that's what they're doing inside that facility there. Imagine some ear protection is needed when that thing is running. Also, we are able to learn more about the telescope with a variety of conversations that we're going to have in this episode. The Roman Space Telescope has the ability to study a wide field of view in our galaxy and beyond. Also a coronagraph to look for planets. A coronagraph, think of it like when we have a solar eclipse. The moon blocks the sun. That's a natural coronagraph, and we can see the corona around it. But in this case, we're so much excited about the corona, we're excited about the planets that are around it. We're looking for distant planets by using a coronagraph on the telescope. It's fascinating. So we're going to talk to a bunch of different people. In this episode, we're going to start with Bonnie Patterson, the Vice President and General Manager for Civil Space at BAE Systems. Give me an overview. This is a new telescope that's about to launch into space maybe very, very soon, later this year. So give me an overview. What is the Roman telescope?
Oh, the Roman Space Telescope is the next NASA Astrophysics Great Observatory after the James Webb Space Telescope. We at BAE are very proud to have partnered with NASA on all of the NASA Great Observatories to date. So thrilled to be a part of this compelling mission that'll help us understand the origins of the universe and also hunt for some exoplanets.
Yeah, we're going to be doing that too because there's a coronagraph on board.
Correct.
So what did BAE Systems do partially with this telescope? What was your kind of portion in that?
So we delivered the wide field optomechanical assembly.
Okay.
Which is the core structure and provides also the thermal environment for the main wide field instrument.
So the wide field instrument, so when we've seen examples, and I can roll some video too, there's a view of what Hubble can see, and then there's a view of what Roman can see.
Yes, 100 times the field of view.
So describe that to me.
Yeah, it's absolutely fantastic. Enabled by the very large focal plane, so the wide angle lens, if you will, on the universe. Absolutely fantastic. We were able to enable that capability with our actuators and precise mechanism capability that we leveraged from the James Webb Space Telescope at the nanometer scale. So we were able to apply that and bring that technology forward to Roman, and that's what's backing that large focal plane array.
That's so cool. So for those that see the picture, okay, it's a very wide picture. That's cool, but what does that really matter and mean for the science?
Oh, so that you can survey the universe, wide swaths of the sky at a much quicker rate than we've been able to do in the past. And also an opportunity to leverage it in parallel with James Webb. So James Webb can look very closely at things that Roman finds across a wide swath of the sky.
One question I also have too is, so let's say we have a big wide picture of the sky and we take that over the course of a year. So we can say some scientists can analyze the top corner, some scientists can analyze the bottom corner, and they can be doing more science at the same time. Is that how it kind of works?
Yeah, that's certainly a portion of it, and it's really utility of the ability to cover wide areas quickly.
Wide areas
at 100 times as fast as Hubble.
So how long have you been working on this?
I have actually had the privilege to work on this for about 14 years now.
Wow, that's phenomenal.
Yeah.
And challenges along the way. Describe some of those to me.
Oh, there's always challenges when you're trying to do something that's never been done before. But, nothing I would characterize as out of the ordinary and in that path along the way.
Any surprises along the way?
There's always a few surprises, but mostly I'm just super excited with the ability to deliver this capability to the scientific community on cost and on schedule. The mission has done programmatically superior things as well. So very excited about that.
And this spacecraft's going to be hanging out in a position not like Hubble that orbits the Earth. This is going to be out at L2 near James Webb Space Telescope.
Correct.
In that
Correct.
kind of neighborhood, essentially.
Correct.
So the challenges with that, are there anything that kind of becomes like more of a concern, like, oh, once we deploy this thing, off it goes?
Yeah, it's certainly a long way away.
Yeah.
And hard to access for sure, but it was designed for that.
Yep, it was designed for that.
Yeah.
Anything else you want to share with us today about the spacecraft, the telescope, the mission, anything, the 14 years you've been working on it?
No, I'm just super
Some stories?
I'm super excited and proud of what we've delivered here in partnership with NASA, and looking forward to the next one beyond this, the Habitable Worlds Observatory, and our ability to take that same technology, mechanisms technology, forward in another, several orders of magnitude to apply to the Habitable Worlds Observatory at the picometer level. So very excited about that.
One question that I just came up with, and I might be asking during the press conference later on or before, depending on how I lay this out in the video, but the question is that there's a lot of excitement right now that just spawned from Artemis 2 and the successes from that. So how do you grab that excitement and bring it to Roman Telescope?
Oh, well, certainly the groundbreaking science that this will unlock for all of us, all of humanity, should be equally as exciting, in my opinion.
Thank you very much.
Thank you.
Appreciate your time.
Thanks.
Thanks. Welcome back to Beyond the Forecast. So on this special edition episode, we're talking about the Roman Space Telescope, and a really cool and fun interview is coming up next. This is with Vanessa Bailey. She is the instrument scientist for the Roman coronagraph at NASA's JPL. We have a great conversation outside of where the telescope is, inside that clean room, learning all about her work and this coronagraph instrument. Let's check it out. So first of all, you must be really excited and really proud, because something that you've been working on for a long time is going on that telescope inside of that room. So how do you feel right now?
Oh gosh, yeah, this has been a long time coming, and I'm thrilled. So I'm on the science team for the coronagraph instrument, and I've been at JPL since 2017, which puts me kind of midway through the project. There are folks who've been working on this all the way since its inception, decades. I'm standing on the shoulder of giants to get to this point, and I'm so excited for the first photons that are going to come in, and within a year we'll be doing science.
Yes, and the coronagraph, give me an overview to a fifth grader how a coronagraph works, and then we're going to talk about the spacecraft specifically. So just give me that overview.
Yeah, well, if you want to see a bird or a plane next to the sun, you put your hand up, block the sunlight. It's the same thing. We're blocking the light of a star to see a planet next to it that's much fainter.
And then, so how are we going to use that on this spacecraft and for this mission?
Yeah, we have very specialized optics, mirrors, and masks within the coronagraph instrument that will block the light of other stars to see planets around them that are maybe 10 million or 100 million times fainter, to see something like Jupiter around our own sun.
So we're looking at distant, large planets surrounding and orbiting, rather, these distant stars. Since the field of view is so wide, are we going to be able to maybe take a look at a bunch of different spots? Is that the idea of this?
Right.
Or are we looking at two different instruments, and am I getting confused?
Exactly. So there are two different instruments on the Roman Observatory. There's the wide field instrument that, will be able to survey the sky 100 times faster than Hubble. Then there's the coronagraph instrument that takes the narrowest of soda straws and looks at individual systems to look for those planets with the direct imaging in great detail. The wide field instrument uses totally different techniques to find exoplanets. Uses something called microlensing, something called the transit method. It will take census of planets around other stars, and then Roman coronagraph will study a few Jupiter-like planets in great detail. They won't be the same planets, but they're going to give us very complementary information about the census of planets and what their properties are. So the technology, the coronagraph technology that we use on Roman coronagraph is kind of the next generation compared to what's on the James Webb Space Telescope or the Hubble Space Telescope or even ground-based telescopes. We're building on all of that heritage. What astronomers can do today with coronagraph instruments are see planets that are maybe 1 million times fainter than their stars, and primarily in the infrared, where those hot young Jupiters are still glowing from the heat of their formation. What we're doing with Roman coronagraph is hopefully getting to 10 million to 100 million times fainter, maybe even a little bit more if in the best case scenario. That might allow us to see light reflected off of the cloud tops of a cold, old Jupiter analog invisible light for the first time. The technological improvement that allows us to do that is not only more specially designing the starlight blocking masks and optics, but also using something called deformable mirrors. Exactly what it sounds like. They are mirrors that have thousands of tiny pistons on the back that can move at nanometer or even picometer scales to correct the very small polishing errors or optical misalignment errors in the system to block out light better, as compared to something like Webb or Hubble that doesn't have those active deformable mirrors. This will be the first time we're using those in space.
How do we know when we're using those deformable mirrors what it needs to be? Is that the system saying, oh, if I want to have this ideal image, I need to deform this way to position A1A versus A3B? Is that how it works?
Yeah.
Kinda?
Yeah. We're using our science camera images themselves. We build a model of how a poke on one actuator on one deformable mirror translates to a little bit more starlight glare in a particular pattern in our science camera image. So then when we see that pattern, we can poke that actuator. Of course, the optimization of that mapping is, the devil's in those details. But yeah, we're using our science camera images to create the commands for a deformable mirror, and we iterate back and forth until we've suppressed as much starlight as possible from our science image and hopefully seeing the little planet.
Fascinating. This thing's going to be launching maybe later this year, and that first image from the coronagraph, what's kind of the timeline for that after we get it into position L2?
After we launch Roman, we have about a 90-day commissioning phase. That means for both the coronagraph instrument and for the wide field instrument, we're tuning them up. We're making sure that all of our capabilities work. We're getting an initial calibration. That takes 90 days. Then we'll transition to regular ops, and at that point we'll start getting to use it for science and for pushing our performance a little bit deeper. Yeah, I mean, I guess this gets back to your former question about how many things we're going to observe. Right, so the coronagraph instrument is not a survey mission. We are going to stare deep for a long time at a much smaller number of things. Think of 10 or tens of systems, not thousands or millions of systems like the wide field instrument will survey. There are some nearby systems, maybe like the Epsilon Eridani system, or perhaps Epsilon Andromeda system, as well as just some of our very nearest solar neighbors that I'm very interested to see. Are they're known to have planets that haven't been imaged before, or some of these systems, like Sean Domingo-Goldman was talking about for the Habitable Worlds Observatory. They may want to look for Earth-like planets around these stars in the future. One of the potential confounding factors there, though, is what if the systems have too much leftover dust from formation? It's too dusty to see those Earth-like planets. This is something that I think Roman coronagraph will be able to help with, because we'll be able to get the deepest images ever in visible light in some of those nearest by systems that might be interesting to look for Earth 2.0 in the future to see, are they clean enough for those Earth finders down the road.
And is that because of the deformable mirror, or why is that?
Yep, the deformable mirror combined with the optimized coronagraph masks combined with the exquisitely sensitive or exquisitely stable telescope. That's something that I guess I haven't mentioned is the Roman Observatory is just wonderfully stable, and it's out in this L2 orbit. It's not going in and out of the sun like Hubble does, so it will be stable, more stable than all of these other observatories that we've built before, and that's what allows us to do starlight suppression at these unprecedented levels.
Did they tap in a little bit of that knowledge from James Webb Space Telescope for the stability for Roman?
I'm sure that's the case. That gets a little bit outside of my expertise.
That's fine.
How much crosstalk there was between those two, but yeah, certainly, there's a lot of heritage there in understanding what kinds of materials are the most stable in space and how do they perform. Like the modeling has been a very important aspect of designing the Roman Observatory, has been developing some of the most precise models of how it will perform under certain circumstances, so then we can design our observations to be constrained within their recommendations for how we can make the observatory even more stable by designing observations intelligently.
And then I have one final question, just kind of your takeaway. We're all excited for this to launch. We're all excited to see, but you've been working on this for so long, so just some final thoughts on that.
Oh gosh, I mean, I think it hasn't hit me yet, if I'm being honest. But that, at this point, we're planning towards launch in early September. And I'm really excited to be in Florida in September to see the observatory launch and to be, collecting these photons that have been traveling towards Earth for years, and to capture them in my detector and get to build a better picture of our nearby solar neighborhood.
As my meteorologist day job, I will try my hardest to make sure during peak of hurricane season there are no storms near Florida.
Thank you.
Launch time, high pressure.
Thank you.
So thank you very much for your time.
Yeah,
nice to meet you too. Yeah. Find out from this instrument, the coronagraph specifically on the Roman telescope, is going to be fascinating. I can't wait to see some of those first images of distant planets around these far stars within our galaxy. And of course, what we're going to see even farther out and beyond that. Finally, Dr. Julie McHenry with NASA. She is the Roman Telescope Senior Project Scientist. She is going to give us some insight of what this telescope is going to do and how it's going to inspire the next generation. That's also part of my question that I asked NASA Administrator Jared Isaacman. Thanks for watching this episode, but we're going to go to those interviews and those talks right now.
Hi, everyone. Current observations hint that our standard model of the universe is incorrect. Roman will be able to confirm these and set us on the path to understanding what's right. We're going to perform a revolutionary census of planets around other stars in our galaxy. We're going to conduct ambitious surveys that will transform and impact every area of astronomy. And we can do all this because Roman's primary instrument combines exquisite performance and sensitivity with an outstanding ability to sweep out large regions of the sky. Previous speakers have mentioned that Roman can survey the sky 1,000 times faster than Hubble. So to put this into context, 1 month of Roman observations would correspond to a century with Hubble. So Nikki mentioned that Roman doesn't do Hubble science faster. Roman will address entirely new, ambitious science questions. So that 1 month of Roman observations could be used to survey our own Milky Way galaxy, uncovering up to half the stars in the galaxy. That would itself result in an astronomical catalogue of objects that is much larger than any that in existence today. And that's with just 1 month of Roman observations. Our main survey will take more than a year. It's huge. If we were to take the single image that is produced from our main survey and try and fully display it with a set of 4K TVs, you'd need more than 500,000 4K TVs. And just to give you a sense of the scale of that, if I was to lay out those 4K TVs, it would cover 45 city blocks. Or to pick something that you actually look at, it would entirely cover El Capitan in Yosemite National Park. I don't suggest we actually cover El Capitan with a set of 4K TVs, but it gives you a sense of the scale. That survey will detect over 2 billion galaxies. And we'll use it to study how the structures in the universe, the stars, the galaxies, the structures of galaxies, grew and evolved. We'll also study how the universe itself has expanded over time. And these are the keys to unlocking the fundamental nature of dark matter, dark energy, and the fabric of the universe itself. Periodically, we'll point towards the center of our own galaxy and monitor hundreds of millions of stars. But we're not going to just image millions of stars. we're going to find a treasure trove of exoplanets, up to 40 times more than are known today. So think of this as the largest census we've ever done of planets in our galaxy. We have a second instrument, the Roman coronagraph. And I think of this as doing magic with physics. We take advantage of the wave properties of light to cancel out the light of a bright star so that we can image faint planets next to it. To do this magic, we have to have an optical system that can adjust itself to maintain sufficient precision. This will be the first time we've had a system in space with this kind of active optics, and it will set us on a path for future observatories to do extraordinary new things. What makes me most excited about Roman is its discovery space. If we have 2 billion galaxies, it means we have 2,000 one in a million objects. We're going to be surveying patches of the sky, going back over and over and over again to find new things that go bump in the night. I very much hope, and in fact expect, that the most exciting science from Roman is going to be the things that we didn't expect, that we couldn't predict, but that will set the new, deep questions for future missions to address. Thank you.
There's something online called the Artemis II effect as part of the Kerbal Space Program community. We're all excited about what happened with Artemis II. Kids I've talked to, fifth graders, I talked to 100 of them last week. They're all really excited. So how do we use this telescope to continue that excitement for the young generation?
Yeah, well, I think it starts with listening to some of the great commentary that Julie just said. I mean, I've got 100 questions coming out of just your intro right there. Look, I am thrilled that the world kind of paused for a moment and took notice to Artemis II, and yeah, I think energized the world's interest in space exploration. Human exploration tends to do that at times, but if it's an opportunity to set the stage for other conversations like Nancy Grace Roman is about to do, that's fantastic as well. We put out some great, like a video reel on it today to get people hyped up about it, and won't be long before this telescope is loaded up on a transport and taken down, and then it's, of course, being launched by a Falcon Heavy. That brings a lot of viewers to take interest, where we'll have opportunities there where, Julie, I sure hope that you're on the live stream for that mission launch to get people excited about the kind of science this mission's going to undertake. So this is great. This is working really well. We're thrilled that Artemis II brought a big audience back to NASA, and now we're going to fill it up with a lot of exciting missions to come. Nancy Grace Roman's next up.